Okay, Physics 15, let's do another one. So we're on chapter 14. I can't believe we've been through 13 chapters already, but we're almost at the end now, so that's good news. So today, magnets and electromagnetism, right? Last time we did currents, before that we did, moving electrons. Well, this flows with that. So let's go. Okay, how do magnets work? Yeah, what is the magnetic field? That's field theory is always rough, right? Here, so here we see a big industrial magnet, and it's picking up metal pieces of some sort, iron pieces. So, interesting. Yeah, no, the way these magnets work, of course, is you apply electricity, the magnet works, they turn it off, and it falls down. So there's the clue, right? These are flow of electrons causes magnetism. All right, well, let's go on with that. So, okay, so we talked about we're all used to magnets to some degree. We stick magnets on our refrigerators. We know and you can feel it. You get the magnet close, and you can feel it pulling. Right, you're like, this is some kind of magic thing. And I talked about, when we talked about electrostatic forces, right, in a previous video, we talked about that, right? Your hair, if your hair is dry, your hair will stand on end, or you can get shock, right? And then, so there's forces that work at a distance, and it's just kind of these invisible forces. Gravity is a field, right? The gravitational field. I throw this pen up, it doesn't just float there. It gets pulled back down because of a field, right? So gravity, though, is only attractive. It only attracts. Magnetic and electrostatic, of course, they can go either way. Electrostatic, two positive charges repel, right? Opposite charges attract. Magnetics is the same. You have two north poles will repel. You can have two magnets. One way you can push them, you can feel the force pushing away. The other way they stick, right? So magnets have a north and a south pole. Electrical things have a positive and a negative, right? Okay. And different kinds of magnets that they're showing here. There's a bar magnet, horseshoe magnet. This is a good one because it'll have a north and a south on one end. That can be useful for certain applications. We'll see. We'll talk about that. Yeah, now not all metals work, right? You probably know that. You have to have some iron, cobalt. We're not so familiar with that, but nickel. We all know about nickel. So magnets, and then things like copper or aluminum, magnets don't work, right? And so you got to have, now you can have alloys with different things. So yeah, so like poles repel and unlike poles attract. Now what's interesting, if you cut a magnet in half, so if this was north and this was south, you cut it in half. Well, this thing is no longer north, and then this one is just south. What will happen is that this, where you cut it, this will become south, that'll be north, and then this will be north and that'll be south. So magnets, if you cut them in half, you retain the north and south poles, right? So there's no such thing, even though the internet is all kinds of nuts that say, oh, the NASA's hiding it, they have just, there's no such thing as a monopole, right? Monopole means just one pole, north or south. There's no such thing. Magnets are dipoles. There's two. You always have a north and a south. So, yeah, like poles repel. Two norths will always repel, but a north and a south will attract. And this just shows that, right? You have a north and a south. The magnets will pull into each other. If you try and push two norths together, they're going to repel, right? It's like a magic force that repels it, right? Some magnets are stronger than others, right? All right, we talked about that. Yeah, you can't have a monopole. There's no such thing. And then the way, a magnet work is that you have these field lines. They will go from the north to the south, and then they go through. Like if you have a bar magnet. A bar magnet is a metal magnet, iron. So the lines will go through. In fact, if you put a magnet on a table and you have iron filings are little bits of iron, and you kind of shake the table, the iron filings will go for, they will form along these magnetic field lines. It's a really cool thing to see, right? And then this is just showing an electric field, where you have a field from a plus to a minus. Although it's different in an electric field, the lines always go here. The lines always go from the plus to the minus. In a magnet, the field lines, when it's outside the magnet, they'll flow in this direction, but if they're inside the magnet, they go up this way, from south to north. So outside the magnet, they go from north to south, but then they go through, so it's like full circles. Whereas if you have like two charges, the lines just go in one direction like that, okay? We talked about electrons a couple videos ago, last video. But there's similarities, right? There's these things called field. Field theory is actually quite complicated. A lot of physics. I was always wondering, well, what are this? When I was in engineering school, when I took physics, I always thought, man, I'm going to learn what these field lines were. I never did. And I thought, I'm missing something. I graduated the class, I got a good grade. In fact, I got my degree, and I thought, I don't understand why this stuff is that way. Well, it turns out, it's very complex. Field theory, so we know how these things work. There's all kinds of math. We make all kinds of machines. We have electric drills and magnets, and we send power, thousands of miles. We know how it works. We're not really so sure why these fields are that way. Physicists are working on it. I'm sure they know a lot, but that's quite complicated. Field theory is quite complicated. Yeah, field lines form continuous loops. Okay, and here's what I just said. I should do this before I talk. All right. Here it's just showing that, say you have a magnet and there's a magnetic field. So magnetic field, they use the symbol B for magnetic field. Electric field, they use E, right? So if you have a magnet, they're saying that it will align itself. You're thinking, what? I never see that. Yes, you do. You see that all the time. Think about it. You all know. Have you ever used a compass? Oh. So a compass, if you have a compass, it has a north and a south in the little compass, and Earth has a magnetic field. So what will happen is that the compass will align with Earth's magnetic field. Interesting. Now think about this. Now what if you made a mechanism where you made your own magnetic field, and you had a magnet in it, and you moved it, and then if you changed the magnetic field, and you kept changing the field, could you make a motor? We'll talk about that later. But interesting. See how Earth's magnetic field has enough force, there's enough strength in that force, that it will move the compass needle. So the compass needle is a little magnet. It's very light, but there's enough force that it'll move it. So, you think that engineers have used that to make electric drills and power and stuff? Yeah, that's how it all works, right? So just always think in those terms. The fact that a compass needle can move, right? Well, then it aligns itself. But what if you kept changing the magnetic field? Could you? Yeah, you could do stuff like that, right? So that's just a little hint for what's coming up. Yeah, so it'll line up, right? They're saying it'll experience a torque. Well, we talked about torques, right? Since this compass needle turns, it rotates. Well, so there's a torque until it's straight, then it'll stay straight, right? Yeah. So here's a good picture of what I was talking about. If you have a bar magnet, and iron filings are just little slivers of iron, and you put it all around the magnet, then you kind of shook the table, right? Or you banged on the table, right? And so there was vibrations, all those little filings, and it's amazing. They will line up and they will show you kind of the field lines. It's really, wow, real physics, right? Yeah, the world is not intuitive, right? The way the Earth, the universe really works is not intuitive. That's why we do science. That's why we do experiments. So now here, look at, okay, what's happening here? So this looks like America, perhaps. There's South America here, Central America. And they're showing, so that would be the North Pole up here. But the magnet's upside down. North, south, no. It turns out that Earth's magnetic pole actually what we call our north, our geographical north, is actually our magnetic south. A lot of people don't know that. Notice the field lines. So just keep that in mind. So your compass that you're using, actually, right, everything's backwards. Now what's going to happen is that we're due to change. About every 80,000 years or so, our magnetic pole swaps, right? It flips. On the sun, it changes about every 11 years. So it's quick. The sun's like change, 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 change. For us, it takes about 80,000 years. So it'll flip. So actually, we're due. We're due for it to flip. In between time, that will be wild. Our magnetic field actually protects us from a lot of cosmic rays and stuff. And also solar particles coming from the sun, and protons and things that come from space. So that'll be interesting times when we lose our magnetic field in between, when it's switching. Maybe it switches quick, 100 years or so, but still, that's like a whole generation of people, right? Yeah, so you can imagine that, Earth has a big magnet inside. It doesn't. What Earth has, it has a molten core. Inside Earth, it's very hot. And there's a very dense metallic core, and it's kind of floating in this hot liquid lava. And, lava is a melted rock. And so they think it's moving in there, and then that causes currents and then magnetism. When you have currents, magnetism follows. We're going to learn about that. Yeah, and also, the magnetic poles are not exactly aligned with the North Pole and the South Pole. They're off a bit, and they wander. They wander a bit. There's a website where you can go and look. So a compass gives you pretty good north-south, but actually if you're doing accurate navigation, you have to adjust for the differences between the magnetic north and true north, geographical north. So. Yeah, and here they're just showing that he showed that if you have a current, here's a battery, and you have a current going, you can deflect a compass needle. So it showed that a current, an electric current, produces a magnetic field. So a current, so you have electrons flowing through, right? Current is positive charge, so the electrons are going this way, right? But it shows that. So electrons flowing through, the movement of electrons causes an external magnetic field, right? That field that is outside of the wires, right? It passes right through the insulation. The field lines go right through that. It doesn't care about the rubber insulation. So. Yeah, and the way it works, so if this is a wire, current's going that way, the magnetic field will do circles. And the farther away you get from the wire, and this is a DC wire, right? We talk about AC, DC, this is direct current. So you have a direct current going through a wire. They call it the right-hand rule. The field lines go around the wire. So you'll have, like, if you have just one wire and you have a direct current going through it, there's a magnetic field all around that wire. Well, that's good to know. And we call it the right-hand rule. And now it's just showing if you have two wires and you have current going this way, current going this way, they will actually be attracted to each other. Okay, and yeah, we're not going to worry about this. I worked as an engineer for a long time. Not once did I ever have to calculate that. So the stuff we did in the last chapter though, when we did parallel circuits, that is important. That you need to know just for life. I mean, you live on a planet where we use electricity for everything, so that you got to know. This, I want you to know the concepts, but we're not going to do that particular calculation. I mean, if you got a job making electric motors for a company, you can revisit that, right? So, all right. So we're not going to worry about these problems. Not going to worry about these problems. Let me move on a bit. So let me go to here. Okay. And what's foil? Okay, this is just showing your magnetic force is proportional to the quantity of the charge and the velocity of the moving charge, and to the strength of the magnetic field. So a moving charge, right? That's electrons flowing. So that will induce a force. You'll have magnetic field. The thing you want to remember is that, you know, electrons are flowing, you know, if you have a charge going in one direction, the magnetic field is perpendicular to that, right? And then the force is perpendicular to that. So if you have an electron going this way, right? So that's your current, right? Here's an I. So that's showing current. The magnetic field doesn't go in the direction of the current. It doesn't go opposite the direction of the current. It goes perpendicular, right? So if this is a wire, right? This thing here is a wire. The current is going that way. The field forces, you know, are coming out of the wire, right? And the electric field, so they're perpendicular, right? The field goes one way and then the force is the other. Everything is perpendicular. That's what you want to know. That's what's important. So, yeah, they call it a Tesla. Let me go back to that one actually. Where was I? We're down here. Yeah. So magnetic field units is they call it a Tesla after the great inventor Tesla. Okay. So it's just good to know that. I'll give him credit for that. Mr. Tesla. He was a genius, holy cow. But he was very eccentric. Died poor. made millions, lost millions, right? One of those guys. Because he put all his money back into his work. One of those guys, he made and lost millions actually many times in his life. What a life that guy had. A bit eccentric. So, okay, let me go to, what am I looking for? Let me hit on this. Oh, no, I don't want to do that. We'll skip the problem. We'll skip the problems. More problems. We'll skip them. Okay. We just talked about that. Yeah, here it's just showing, though, that your magnetic field and your forces are perpendicular. Just know that your field and your forces, they do not go into the direction that the electrons are flowing. They go perpendicular. They go at 90-degree angles to that. That's what's important. That matters when we're learning about electric motors, which we're going to be learning in a bit. So, okay, let's keep going. So now we talked about electricity moving through a straight wire, but what if you had a battery over here and you had your wire going, you made a loop and it came back to the battery here. So it's direct current, right? So electrons are flowing, right? Well, what will happen is that, now remember we did the right-hand rule. So if your current is going through the loop this way, your magnetic field is going to go this way. And this part, right, it's a right hand, so it's going to be this way. When you're coming back, now it's going to, look what happens though. So look what happens to the magnetic field. It's going in this direction. When it's coming back, it's in the same up, right? It's in a counterclockwise direction. Here is clockwise, but it's the same up here. So it builds. So your magnetic field got stronger because it's building from this loop going this way, and then on the way back, it's going this way. We just learned about that right-hand rule, right? If current is going through a wire, the magnetic field, why it does that, man, that used to bug the heck out of me, why it does it. It just does, okay? Just the way gravity works. The field lines work that way, right? It just does. So, and then some physicists might know, right? Field theory, like I say, very complex, right? Okay, so the current goes this way. So my thumb is pointed into the screen. My fingers are going this way. So the magnetic field goes this way. Coming back, now my thumb is pointed out of the screen, pointed towards the camera, towards this camera. And the field lines, magnetic field lines are going this way. B means a magnetic field. Look, it builds. So this makes a stronger magnetic field in the center. Aha. You think engineers use that to their advantage? Yeah, you bet they do. Yeah, so what happens is that you can, this thing acts just like a magnet. If you had a bar magnet, right? A hunk of metal that was a magnet. So you have your north, south, north, south. If you have a loop, now this thing behaves just like a magnet because your electrons going through. Then you always have, where you have charge, where you have electrons flowing, then you have an associated magnetic field. That the two always happen that way. You can't have one without the other, right? Okay? Oh, let me keep going. Let me go here. We'll go back to this. Okay. Now, so here what they've done, here they've had, so you have an external magnetic field, right? So there might be big magnets like on this side, you have an external field, and here what they've done is they put a loop in, but the loop is at an angle. So this thing has current going. Well, it's going to make its own magnetic field. It's like a compass needle. And if you have an external, so say you have a big industrial magnet with a north and a south pole, well, now this thing is going to want to align. This field is going to want to align with that field the same way a compass needle aligns, right? So always think about the compass needle, right? Because that's easy to think. But this is interesting. So could you make a device where you could turn stuff with a magnetic field? That's how drills and blenders and stuff work. It's a little more complicated, but that's the basic. This is what they're saying here. Let me go back. Let me go back to that one. I wasn't done. Okay. So we'll just look at the picture, right? So we'll look at the picture again. Okay. So yeah. So if you have a magnetic field going this way, say there's a big horseshoe magnet out there. You have a north and a south pole. So you have a magnetic field going through the poles. And if you have a loop, well, now this thing we just saw previously, this thing has its own magnetic field. Well, it's going to want to align with this field the same way a compass needle does. So this loop, this wire loop, will experience a torque. It's going to want to bend depending on how strong the magnetic fields are, right? All right, now I want to get out of that. We'll go to the next one. And this is saying more of the same. This is saying more of the same, what I just told you. Yeah, so then you could use something like this to make a meter where the amount of current that's going through is going to move, right? So yeah, so of course all kinds of clever things would be developed. Let's look at this. So you can make a motor, a simple motor. Here you have a battery. So you have DC current going through your little loop, and now so that makes its own little magnet, right? We just saw in our previous pictures where you have a battery, you have current going through this loop, but now you have a big horseshoe magnet here, and then so a north-south. So there's a magnetic field going from this north to this south. If you were to rotate this loop, well, now you're fighting, so you're having two magnetic fields fight against each other, right? Or maybe you could do something else clever, right? Let's think about that. So that's what they mean by torque. Torque is if this thing isn't already lined, it's going to experience a rotational torque to align it, right? Yeah, so now if you have it, so what they're saying here now, so say this loop, say if it was able to turn. Yeah, you can do that if this is on an axle. And then if your wire connections, instead of it being a solid wire, if you had brushes. Brushes mean that you'll still have your electrical connection, but it's able to rotate, right? So an electrical, the brush means that you'll have current, you'll have your negative terminal of your battery connected here, your positive here, and then what will happen is that it will turn this loop. But if you have a brush, when it gets to the other side, then it's like the current is alternating, so it's like a DC, so you can keep this thing turning. And a brush means that even though it's turning, charge, the electrons will go through it, right? So there's a little bit of friction there, but it'll turn. You can make a simple motor that way, right? Because it turns, And then when it's aligned, well, then if you switch the direction, you can keep it turning, right? Because it's going to want to align. But if you switch the current, so what happens is that the current's going one way in a loop, and then just as it's coming around, then the way this thing is built, now it'll switch, and now the current's going the other way, so you can keep this thing turning, okay? So it's a simple DC motor. Now look what happens if you do a lot of loops. And so we were just talking about one loop. If you did a lot of loops, guess what? Your magnetic field gets way stronger. So rather than just do one loop, that's okay. But if you do a whole bunch of loops, you can get a really strong magnet here. That's how they make big and strong industrial magnets, right? So all the loops add together. You can get a really strong, much more. And then if you put a metal bar, an iron bar in there, that makes it even more stronger, because air doesn't work so well. It doesn't carry a magnetic field as well as an iron bar. So if you put an iron bar in there and then had a wire, and the wire has rubber, you know, so the electrons will stay in the wire. You have it insulated. You'll have a way stronger magnet. Yeah, when I was a kid, I've done this a lot. You just have a wire, you wrap it around a nail, put it on a battery, and you can make a magnet and pick up things, right? It's called an electromagnet because you've made it using electricity, so they call that an electromagnet, as opposed to a permanent magnet. Permanent magnet is what you stick on your refrigerator, right? You know, they're talking about primary coils, secondary coils. Yeah, so it turns out, okay, let's go through, we're not gonna. Yeah, so you can make a current the other way. Instead of having a current, before we had a battery here and we ran a current through the wire, so electrons were moving and that made a magnetic field. Well, what if you don't have a battery? What if instead, now this is just a meter. This is just a meter that's gonna measure the current of this. Well, if you put a magnet in there and it's just still, you don't get a current. But when the magnet is moving, then you get a current. So this was a huge discovery. So it works the other way, because when you have a battery, the electrons are moving and that makes a magnetic field. In order to do it the other way, where you have a magnet and you put the magnet and you want to create electrons, you have to keep the magnet moving. Aha! That makes sense, okay? One way or the other, you got to have movement. So you have to move the magnet, then you produce electrons. All right, we're just talking about flux. We already talked about that. Okay, and yeah. Okay, we're not going to do this. Where are we? We're here. Alright, that's all very interesting, but we're going to go to the important stuff. So let's go to generators and transformers. So putting together everything that we've learned, if you have, now you have permanent magnets, right? So here you have permanent magnets, okay? And you have, inside there you have coil, so inside there then, you rotate. So where is the force coming through? The force now is coming through that you are rotating. Let's go down. So this is a generator. A generator generates electric currents, right? Now here it's going to do an alternating current. So it's going to go in one direction and another one. A simple generator consists of a coil of wire that generates an electric current when turned between the pole faces of permanent magnets. So you have permanent magnets. The coil's rotation, remember I said you have to have movement, causes the magnetic flux through the coil to change continuously. So now you have a change in the flux. It's this changing flux that produces a current in the coil, right? You have to have a change. But where is the work coming from that produces electricity? Here it's this hand putting the work in. So you can make electric current now using magnets and the coils like we talked about. So it's the inverse of the other way, right? And here you're turning it, so you're making the coil move with permanent magnets, and that'll produce an electric current. And you can have an AC current. We talked about that last class, right? So the current goes in one direction, another. So here's where the coil, right? The coil is at its maximum, and then when it lines up, there's no current. But now the coil is in the other rotation, and the other rotation, right? So when the coil is lined up, there's no current. But then quickly, it's going the other way. So you get an AC current. I should show it this way. This is the voltage. This is the voltage here. So the voltage goes from your maximum through zero to a minimum. But this is, it's just a voltage in the other direction, right? So that's AC current, or AC, yeah, that's AC. Now, what is a transformer? When you have these when you have wires outside, right, on these poles and stuff. Well, first of all, you have these huge. When they have a power plant and you have those really huge towers, those voltages are really high. The reason is the higher the voltage, you can send more power with less resistance. Remember, I squared R. So the more current you send, you'll use more power up just in sending it, because it's going through the wire, through the resistance of the wire. But if you have a higher voltage, you minimize your RA square R losses. If you're going, what? Make sure you watch my previous video again, right? A transformer is a way, so you have these really high voltages. Well, in your house gets like 240 volts, and then because your washing machine can actually use like 240 volts, but then in your house it's 110. So what you do is there's 240. And then your house is between like 110 and 120, like 115. It uses half of that, right? We're not going to get into those circuits. But transformers are the way to step down the really high voltage so that the electric companies use. Then you'll see these devices up on the poles and stuff. What it does, it's bringing the voltage down from a very high voltage down to a lower voltage and then sending it to your house. The devices that do that are called transformers. So how do those things work? Yeah, so for your house, it takes the voltage down, because the wires actually, so they're dangerous, right? So the wires that are, you see, these poles, electric lines running outside, it's very high voltages. It gets stepped down before it goes to the neighborhood, so that you can use in your house. You can just plug in and you have approximately 115 volts there, right? The way that works, there's an alternating current. So you're inside those transformers that are up on the poles and stuff. You'll have one side that has a lot of windings,